Okay, Chen, what one were you looking at? Actually, put this here. Nothing massive that I can put out there, huh? Yeah. That's okay. It's okay.
So for question number 10F. So for this one, I'm not sure I'm doing it right because we do set the
Yeah, if K1 equals minus K2, that means the waves are traveled, same wavelength, opposite directions. And you know from your work with waves on a string, that's just a standing wave where it goes up and down like this, right?
yeah, but the so the probability density does not depend on time, and the my answer looks something like this. That's the probability density. I'm not really sure whether this is right or not because there's a imaginary bar over here. If you square it,
Right.
it disappear. And what I'm confused is because you say is maximum minimum in terms of M and K, but it doesn't really depend on N in my answer. So I'm not really sure on whether I'm doing it.
You know, without looking at my work, I wouldn't remember how M comes in there. 11, huh? 10, 10F. Yeah. I think I just put M in there because M was a parameter in the problem, but it doesn't depend on it. Okay, sounds good. Mm-hmm. Okay, so I just remembered at the beginning of this week that we have a break day on Wednesday. I'm sure you all are very aware of that, and that's great. My plan is I'm not really sure what we're gonna do between Thursday and Friday. I want to start working on MATLAB stuff, so like get you started on something, and then you're gonna finish a project that we're welcome to talk about outside of class. But I may do that on Friday, in which case we would meet over in the electronics lab. And I'm waiting to see if Alvis has access to MATLAB too, but that would be the idea for that day. You do?
Yes.
Okay, good. Turn up the speaker. You're a little bit quiet. There we go.
No, I think it's there we go. I think it's just that my microphone was distant.
Okay. Also, I have the exams and I'll give them back at the end of class. You guys did great as a whole, so I'm not too worried about where we are, at least on the average. So we can talk about those just in the last minute or two of class. Any other concerns before we jump back into the Dirac delta function? Well, maybe it's worth reminding ourselves where we were. Yichen was just asking a question on the homework that's due today. And I can stay after for 10 or 15 minutes if anybody else wants to talk about those 3 homework problems. So let me know if you need more time to do them. So where we were talking about the Dirac delta function well, and we split it up into two kinds of problems. We first found the bound states for it. And from our general discussion of bound and scattering states, we said whenever the energy of the state you're considering or looking for is below the asymptotic value of the potential on both sides, that means it's going to fall off to zero as you go off to plus or minus infinity. And we're talking about a bound state that is basically going to be localized in one region of space rather than free to go off to plus and or minus infinity. And we found out that there was only one bound state, and it looked like this. This is what the bound state lowercase psi looks like. It has a cusp in it. It's exponential increasing on one side, decreasing on the other. And through some trickery of integrating across the x equals 0 region, we were able to find the allowed energy of that bound state. So there's only one allowed bound state energy. And there it is. Okay, and so then the question is, well, there's probably an awful lot of scattering states. The claim is that if you take any shape for psi of x and 0, you should be able to write it as a linear combination of all the definite energy states. If we've only found one bound state that's a definite energy state, I can easily choose a psi of x and 0, maybe that's square, that's not going to look at all like this. And it's going to have other stuff mixed into it, other definite energy states. So we were in the middle of finding the scattering states, and here is about where we were. Now, this is just like the harmonic oscillator difference. And if you make our usual for k, and we could have written it as a linear combination of cosine. Okay, as traveling waves, where it will actually be to our benefit to write them as a linear combination of e to the plus or minus I kx. Okay, and again, k here is greater than 0, or at least it's non-negative, right? I guess k could be 0, but it's non-negative because the square root is definitely non-negative and the denominator is non-negative. So we're thinking of k as being a positive quantity. And now the only question is, well, what to do with all these undetermined constants in here? A's and B's and F's and G's. And in thinking about those, oh, and I should also mention that here at the end of Friday, I was a little bit confused about something I stated, and that's because in my notes, I had labeled these backwards. I had this one labeled as x greater than 0, and this one labeled as x less than 0. It should be negative x is the top one in the notes, and positive x is the bottom one in the notes, and that makes everything I'm saying make sense as far as I can tell here. Okay, so we've got to do to reduce these. Well, okay, we solved the differential equation in the two regions, but we got to connect them up using the continuity condition. That's pretty easy to apply. So that's one condition on these four undetermined constants. And the second condition is that weird one where we integrated across, from minus epsilon to epsilon of the time-independent Schrodinger equation. We got this condition. And you can just figure out what psi is at x equals 0 on the two sides, right? It agrees on both sides. And then figure out what the change in the derivative is. And this is what it reduces down to when you do that. Okay, it's not my favorite equation, but it's another condition. 4 undetermined constants and 2 conditions leave still 2 undetermined constants. I could get rid of B and G or something like that, but the question is what to do. We're used to having 1 undetermined constant if we're talking about a traveling wave, because that would represent the amplitude of the wave, right? But here we've still got 2 undetermined constants, 2 equations for the 4 unknowns. We talked about how when you look at this e to the I kx, and again, remembering that for our definition of k is positive, we know that this is a wave traveling in the plus x direction. Because when we put in the time dependence, it's e to the minus I et over h bar. and that represents a wave traveling definitely to the right. And this kind of thing represents a wave traveling to the left. So if we think of a typical scattering experiment, usually the beam is coming in towards your target, that we're thinking of this delta function potential as kind of a target. We're going to shoot a beam at it and see what sprays off of it, right? We want to detect the outgoing kind of energy that's coming out of it. So we might just say, well, if we're going to send a beam in, we'd probably send it in from one side. Usually you're not shooting a beam at a target from both directions. And so Griffiths just says, let's imagine that the beam is coming in only from -infinity towards 0, which is where our target is. That's just the direction we're shooting the beam. We're not going to shoot a beam in from the positive x-axis towards 0. That's just a choice we're going to make. And that means there should not be, in our scattering experiment, any component of a beam traveling in the negative x direction for positive x. We're just going to imagine we're shooting from the negative x direction. So there shouldn't be anything coming in this direction on the positive x side. And that means in our, once I've changed these to the correct thing, that was what was confusing me on Friday. Once I've changed these, that means for positive x, I shouldn't have any beam going in the negative x direction. And this is a traveling wave going in the negative x direction. And so we're going to take g equals 0. And then the interpretation of the other three coefficients is A is a wave that's in the negative x direction going towards the origin. That's the amplitude of our incident beam. And then B is a beam in the negative x axis side traveling to the left, traveling towards -infinity. That would represent the amplitude of the wave that's scattered off of this delta function potential and is heading back towards -infinity. And then F would be a wave in the positive x direction that's heading off towards +infinity. That would be the component of the wave that got through the target and is heading on towards +infinity. And again, we're setting g equals 0. So those two equations that were kind of ugly before, that gives two constraints on 4 unknowns, plus we're throwing away g because that's a typical kind of scattering experiment where you have a beam coming from one direction. That will leave us only one undetermined constant. Okay, so we've got these two conditions and g equals 0. You got to do some algebra. It's not the most exciting algebra, but that allows you to solve for b in terms of a and f in terms of a. So there's only one constant left, and we're going to express everything in terms of a. And things simplify a little bit if you make this change of variables just to beta is m alpha. Remember, alpha was the strength of our well. It's the minus alpha delta of x over h bar squared k. Or, if you write k in terms of energy, right? I use k as √2 me over h bar, and you substitute that in. That's beta is just a function of e. So if I know beta, I know E. If I know E, I know beta. It's just another way of parameterizing that. When you solve this, the claim is that this is what B is in terms of A. It depends on the energy. And this is what F is in terms of A. So we can find in terms of the amplitude of the incoming wave, what the amplitude of the two outgoing waves is. The one that gets scattered back towards -infinity and the one that gets scattered forward towards +infinity. We've got those amplitudes. Okay. Then the question is, what are we going to do with those amplitudes? And the problem is there's no way to determine A. If this were a bound state, we would just normalize it. But these are not normalizable states. E to the I kx kind of things just don't have a finite area under the psi star psi curve. So how are we going to interpret them? And the way we're going to interpret them is to think of the probability of finding a particle in a little region of the beam is going to be proportional to the amplitude squared of that beam. In other words, probabilities are proportional to the magnitude of psi squared. And when we take the magnitude of e to the I kx squared, that goes away. So all that's left is the coefficient of that part. So we're going to define The reflection coefficient is the relative probability, of being scattered. In other words, what's the probability of being in a region of the scattered beam that's scattered backwards relative to the amplitude probability of the incoming beam? So this is like relative probability here and that one. So I'm going to plug that in terms of beta. If you take the magnitude of b squared over the magnitude of a squared, notice I could just divide by a and then take the magnitude squared of this. When you take the magnitude squared of a complex number, you multiply it by its complex conjugate, and you'll see you get this expression down here. That is a function of energy because beta is a function of energy. There's definitions piled on definitions here, but if you use that expression I wrote down on a previous plot a slide for beta as a function of energy, here's what it is as a function of energy. And we're going to call that the reflection coefficient. It means the probability of an electron or whatever the particles that are comprised of this beam coming in, the probability that it's going to be reflected back in the direction that it came. Okay, and that's just the square of the amplitude of the outgoing beam towards minus infinity to the square of the amplitude of the incoming beam from minus infinity. Okay, and we've got it as a function of energy. Similarly, we're going to define the transmission coefficient as the ratio of the square of the amplitude of the outgoing wave to the right for x greater than 0, the one that's heading off towards plus infinity, divided by the square of the incoming beam's amplitude. And again, we can get that by dividing by a and taking the magnitude squared of that. You see it's just 1 over 1 plus beta squared. And there it is as a function of energy. And so I guess one thing to notice is that they add up to 1. Of course, the probability or the fraction of particles that are reflected and the fraction of particles that are transmitted better add up to 1, right? If one is 2/3, the other one better be 1/3. We can also see the behavior as a function of energy. As energy gets really large, this denominator is going to get large and the fraction is going to get smaller. So the reflection coefficient goes down as energy gets large. The transmission coefficient you can think of because energy is getting large. This is getting small and the transmission coefficient is going to 1. Okay. Now, once we've done all that stuff, if we go back and look at what these states look like, this is something that's not visualized in Griffiths, but let's visualize it with a little MATLAB simulation here. And it takes a minute to kind of unpack what we're doing here, but this is the usual representation where I'm plotting the real part along the direction into the screen, imaginary part of psi going up like that, and this is x going along here. The delta function potential is right at the origin, and the blue corkscrew that looks like it's heading to the right, that's our incoming beam. It has a certain amplitude. We don't know what the amplitude should be, but what we're concerned with is the amplitude of that beam compared to the amplitude of the beam that looks like it's traveling to the left for x less than 0. That's the backscattered beam. And also the beam that's shown here in red that looks like it's traveling on past x equals 0, that is the forward scattered beam. And when we apply those conditions to make the function be continuous across x equals 0 and have that discontinuity in the derivative, remember we said that there's a discontinuity in d psi dx from x less than 0 to x greater than 0. That's what you're seeing with that kink in this function. If we add together the two functions in the x less than 0 region, what we're getting is the red function for x less than 0. So this is a particular scattering state for a particular energy. I happen to have chosen an energy that gives beta equals 1. Okay, that's a particular energy. Beta equals 1. And so when I choose beta equals 1, that determines what the amplitudes of all three of these waves in these three regions are. And then I can just add together the two waves that are moving in opposite directions for x less than 0 to get the total wave in that region. So the red wave is a particular definite energy state, solution to the time independent Schrodinger equation with the time dependence put into it, right? So it's sort of rotating around as time goes on. And you can see that kink at the origin where we know because the potential goes to infinity there, we shouldn't expect the derivative to be continuous across there. What happens as I change beta? Well, here's a small beta. When beta is small, that means the energy is large. So this is like large energy. Notice now that relative to the incoming wave amplitude, that's the amplitude of the blue curve that's moving to the right, the amplitude of the backscattered wave is really small. So that means the reflection coefficient should be small here. And the amplitude of the wave to the right, the positive X region, is almost the same as the amplitude of the incoming wave. And that means it's almost all transmitted for this energy. And similarly, if I take a larger beta, large beta means small energy. So for low energy, almost all of it is reflected. Hardly any of it is transmitted. But what we're looking at here with those red curves, I know it's a little bit complicated, but those are our definite energy scattering states. And there's a continuum of them, right? I could increase the wavelength just a tiny bit and we would have another one. Increasing the wavelength would correspond to decreasing the energy of the state. Okay, so they're not just E to the IKX functions. They're different in the two regions here.
Question.
Question, yes, Alvis?
I can't see the presentation.
Oh, I'm sorry. Yeah, feel free to just yell out if that happens in the future. Now you can see it.
There we go. Thank you.
So sorry about that, Alvis.
Oh, no worries, no worries.
Click on this again. So again, this is a low energy case where the transmission coefficient is very small. The reflection coefficient has to be large. It's almost all reflected back, as you can see for the blue curves there. Okay, just a couple more comments on the scattering states and the whole collection of states. There we found one bound state, and then we got a continuum of scattering states. All positive Ks are allowed, so we have a continuum of those. They're, of course, not normalizable. We never found out what A should be for those states. We were able to write the other constants in terms of A, but we don't know what A should be. And therefore, they're not physically realizable single particle states. In other words, we're thinking of this as a beam coming in from the left. And we shouldn't, there's no way to put a single electron into a beam state that just goes all the way from minus infinity up to the origin. So there's no way that we can put a single particle in these states. But as we've seen before, we can put, just like for the free particle, we can put a single particle in a superposition, normalizable superposition of these states. What I had written in the notes was this. If we take an arbitrary psi of x0, you're going to need both the bound state and all of these scattering states to make a complete kind of basis out of which you could write this as a linear combination of them, right? So I'm saying add up little bits of the psi of k with different coefficients. Let's add them up for all the k's from 0 to infinity. So this is a k integral here. Plus, we might need some of the bound state in there too, because without all the pieces, it's not a complete set. In other words, we can't write an arbitrary function as a linear combination of those. Just like if you're in 3 dimensions, if you're missing z hat, or if someone only gives you 2 of the 3 basis vectors, whatever they are, you can't write an arbitrary vector in terms of 2 basis vectors. You need all 3. And so this is an important piece that we keep that in. So for an arbitrary psi of x and 0, it might be some linear combination of those. Now, if it's a scattering state, this coefficient would probably be 0. Okay, now here, this raises kind of a confusing question. If we take this superposition, and let's imagine for the moment that C bound is 0. So we're really talking about a scattering state, but it can't be a definite K state. It's got to be a linear combination of some different Ks. That means it contains different energies. The transmission and reflection coefficients depend on energy. They depend on K, and therefore they depend on energy. They depended on beta, which depends on energy. So if you can't be in a definite K state, there's no definite energy that your state has. It's a linear combination of different energies. And therefore, how do I figure out what the reflection and transmission coefficients are? And there's a way to make sense of that, but it's not worth it, because generally when you do have a beam, you tend to put it in a very, very, very narrowly peaked superposition of only a very narrow region of Ks. And so if we are saying, as a function of K, I'm just going to have almost all 1K with just a narrow spread around that, what we're going to do is just evaluate the reflection and transmission coefficients at that K value, which is most likely, and not worry about what to do for the other cases where I have a weird scattering state that is, the incoming beam is a weird linear combination of lots of different energies. That's not usually the way scattering experiments are performed. So practically speaking, we won't need it. The magnitude, so we've been talking about single particle states. You can also think about these scattering states as being beams containing multiple particles, and this comment just talks about ways to think of that. Normally when you have a beam, you have a lot of different particles, and if you have, effectively an infinite number of particles, you don't necessarily have to think of the a wave function doesn't have to be normalizable anymore, as long as the density of the particles in the beam isn't too large. I'm probably not going to say more about that, but I'm happy to talk about it outside of class. I don't know that Griffiths mentions much about that. He does mention this. If you remember, our potential was minus alpha times delta of x was our V of x. So that was a potential well going down at x equals 0. If you change minus alpha to alpha, in other words, we're talking about this potential, you could just have, you're thinking of it as a very narrow barrier kind of potential, and you could study the scattering off of that. And you find out that the reflection and transmission coefficients, strangely enough, are unchanged just by looking at the problem and just saying, oh, I'm just going to flip alpha to minus alpha in all the work that we've done and see what happens to the solutions. And we find out that that it can, the transmission and reflection coefficients are unchanged. Now, classically, of course, this is an infinitely tall barrier. So if I sent a physical particle at this, I expect it to be rejected every time. And that means that we're seeing the effects of some kind of tunneling here in the quantum mechanical case, where the reflection and transmission coefficients aren't necessarily just 1 and 0. Okay, that was kind of a lot to finish that off, but we're seeing the pieces of what we're now going to piece together in the finite square well. It's a little bit more complicated solution, but we want to concentrate on the big picture. We're going to separately find bound states, the ones where the energy of the state that we find for a solution to the time-independent Schrodinger equation is asymptotically below the potential on both sides, and scattering states where it is above the potential on one side or the other or both. And let's just try to view this solution at a high level. I mean, the details are in here and certainly in Griffiths, but you have to kind of grind through. And there are a lot of cases where he does some algebra and doesn't show you the work in between. So we're going to look at now the finite square well, and I think you looked at the form of the solutions for this. So it's the potential is going to be 0 everywhere except between minus a and a. And in between minus a and a, it's going to be constant minus V0, where V0 is a constant value. So V0 is positive, minus V0 is the depth that it goes down to. And as before, we're going to start by finding bound state solutions to the time-independent Schrodinger equation. And of course, we're going to have 3 regions, right? X less than minus a, between minus a, and x greater than a. So we've got to solve the time-independent Schrodinger equation in those 3 regions. It's easy every step, but there's just a lot of steps to put together. So if you write it for the, x less than minus a region over there, v of x is 0. It's our usual harmonic oscillator differential equation. I'm sorry, exponential growth and decay. I'm sorry, we're looking for bound states here. And that means the energy is less than the asymptotic value of the potential, right? So our energy is down there. And that means that this energy right here is a negative value. And so when I put this stuff over on the right-hand side next to the energy, I'll get a minus 2me over h bar squared, but E itself is negative. And so minus E is positive. And so we're going to make the same definition we made before of kappa. Kappa has the minus sign under the square root because E itself is negative. So with the extra minus sign, the thing under the square root is positive. So this is not the harmonic oscillator differential equation. This is exponential growth and decay differential equation, right? Linear combination of exponential growth and decay. E to the kappa x and e to the minus kappa x. Okay, so our general solution is going to be a linear combination of those, but we're immediately going to throw away the exponential decaying solution. Why? Why did I X that out? Or why is Griffiths going to immediately say, let's throw that away? Yeah, we're looking for normalizable bound states, and this part's going to make it normalizable because we're talking about negative x, the region of negative x that goes to minus infinity. And this blows up as you continue to the left. So we're just going to say, we got to take a equals 0, or we're not going to find a normalizable state. But it's fine if it keeps getting bigger as we go to the right, because this is only valid for x less than minus a. We don't really care if the fact that it's getting bigger because it gets cut off at x equals minus a, and then we have to do it in the other region. Similarly, for the region x greater than a, it's got to be only exponential decay over there. We throw away the exponentially increasing one in that region to make it normalizable. Finally, in the middle, we write down the time-dependent Schrodinger equation, the time-independent Schrodinger equation. And in that region, E is greater, or you're going to get an E minus V0. And so you will, E plus V0, E plus minus V0. So you'll get an E plus V0 on this side of when you solve for d psi squared dx squared. And maybe we better work that out because let me stop sharing here and let's work it out on the board. What about the middle region? Okay, so we're talking about, again, bound states. So we're talking about an energy kind of in this range. This is potential minus V0 down there. And when we write down the time independent Schrodinger equation, we get minus h bar squared over 2m second derivative of psi with respect to x plus v of x times x. And in the region we're trying to solve it here, so we're doing minus a is less than x is less than a. That's the region we're solving it. V of x is minus V0 times psi equals E psi. And as before, just to see where things are, let's solve for d squared psi dx squared. When I put this piece over on this side, it gets a plus sign, right? So I'm going to have an E plus V0. And then when I put this stuff over on the other side, I get a 2m times that with a minus sign out in front from this minus sign divided by h bar squared. All of that is multiplying psi, and that's the second derivative of psi with respect to x. Now, what to think about this minus sign or this thing here? Let's see. E minus V0. This energy level minus this energy level would be E minus V0. That's E plus V0 is positive. This thing is positive right here. And that means if I'm going to make a definition, the definition I want to make, my shorthand definition, should be the square root of 2me plus v0 all over h bar. So that what's sitting out in front here is minus k squared psi. We can't put the minus sign under the square root with it because then we'd be taking the square root of a negative, and at least it would be confusing to think about the differential equation. So here's our harmonic oscillator differential equation. And the solution is a linear combination of either positive and negative exponential traveling wave solutions. Put this back up here. Or in this case, for reasons we'll see shortly, we're actually going to choose to write it as a linear combination of cosines and sines here. It's actually going to help just with the algebra. We're always write it as either a linear combination of cosines and sines or e to the ikx and e to the minus ikx kind of stuff. And I'm sorry, I'm following Griffiths here. He doesn't define this thing to be k because it's not our usual k definition. Griffiths defines it to be L. So instead of cosine of kx, we have a cosine of Lx, just because he wants to stick with the usual definition of k. All right. So here's our solution before we started simplifying much. We threw away the terms that were obviously non-normalizable, like the one I X'd out there, the one I didn't even write down there. We've still got 4 undetermined constants here, right? B, F, C, and D. But we haven't applied any boundary conditions. We have 2 boundary conditions to apply, one at x equals minus a and one at x equals plus a. And we're expecting the psi should be both continuous and its derivative should be continuous because the potential doesn't go to infinity anywhere in this problem. Okay. Now, in applying the boundary conditions and finding the solutions, and actually this might become a little bit more clear when we do our MATLAB work. When you have a symmetric potential, like a potential that's symmetric around x equals 0, the solutions to the time-independent Schrodinger equation will always be either even functions or odd functions. And we've seen that happen in a couple of cases so far. And you might stare at the differential equation and figure out that that's can generally be assumed. So we're gonna take the cases separately, find even solutions to it and odd solutions. That only works because our potential was symmetric about x equals 0. If it weren't symmetric, it wouldn't be broken into just even and odd solutions. They wouldn't necessarily have any parity with respect to the origin. Okay, so let's take the even solutions first, and the odd solutions will be just as easy as the even solutions. Okay. In the middle, if I'm looking, remember, this is the middle region from minus a to a. If we're looking for even solutions, obviously c has to be 0 because we're saying psi is a linear combination of an odd function and an even function. If we're looking for just the overall even function, then this middle part has to be even, and therefore c has to be 0. That's why it's thrown away down here. So we've got, and again, I'm not sure why, I'm probably disagreeing with how Griffiths is labeling these, but in the positive x region, you've got exponential decay. In the negative x region, what we're going to do is figure out how f and d have to be related, and then we'll know that if I want to figure out what it is for the negative x region, I can just use the fact that it's symmetric. Psi at an x for x less than 0 is the same as psi at minus x, which is what it's doing at positive x, which presumably we've already figured out. So we want to figure out not only how are f and d, how do they have to be related by applying a boundary condition at x equals a, but also what the limitations on kappa and L are. Kappa and L are both related to the energies, so how are those constrained? And here's where it gets a little bit confusing. So again, try to stay with the high level picture. We're going to apply continuity of psi at x equals a. That's easy enough to do, right? Plug in x equals a into both of these and set them equal. That's what we're doing there. And the derivative of psi has to be continuous at x equals a. So take the derivative for x greater than a and the derivative for x less than a and set them equal. Nothing mind-blowing there. We get things that are functions of the coefficients and the kappas and the L's. What are we going to do with that mess? Well, here, let's just follow what Griffiths suggests that we do. We're first going to try to look for the allowed energies of this. And that means the allowed values of kappa and L, because kappa and L are what determines the energies here. So Griffiths says, let's take these two relationships and divide them out. You can see that the exponentials then will cancel out if I divide the sides. The F's and the D's will cancel out. And that means I'll get a relationship that only depends on kappas and L's, which is going to be a hidden relationship that determines what energies are allowed. Okay, so when I divide both sides, the exponentials go away. I get a kappa on this side. The minus signs cancel out. And we get sine divided by cosine is tangent. So it looks like I did the second one divided by the first one. Okay. And just to make things, because there's an LA as the argument of the tangent, let's multiply the left and the right-hand side by A just to get things in terms of kappa A and LA. Okay, this really is something that is an equation that constrains what the energies can be, because kappa and L depend on E. But it's hard to, thankfully we have Griffiths to follow along here, which is, he's following somebody else's nice way of thinking of this. Kappa, here it is, explicitly as a function of E, and L as a function of E. So this is a condition on what E can be, and there's only so many solutions to that equation. What Griffiths suggests is that we change variables. So ignore what's down here for a second and just look up here. It looks like this is a function of L times A, right? There's an L times A over here. So maybe we should call that L times A a new variable. Let's just change variables and call L times A Z. Okay? Now, if you take A squared times kappa squared and work out what this side is, and you take A squared times L squared and work out what this is, right? Square this and multiply by A squared on both sides. You'll find when you add those two things together, you get this mess over here, okay? And so this tells us something about, so we're going to call L times A Z and try to figure out, instead of what the allowed values of E are, what the allowed values of Z are, and then we'll reinterpret later in terms of E. So it's true that A squared kappa squared plus Z squared is equal to this mess. And Griffiths says, let's just call that Z naught squared, the square of Z naught. In terms of those two variables, then if I solve for A squared kappa squared and then take the square root, this is the relationship between kappa A and Z. And now what we're going to do is just solve that for the allowed values of Z in this equation up here. So I've got an expression for the left-hand side can be rewritten in terms of Z. And the right-hand side can easily be rewritten in terms of Z. It's just Z times the tangent of Z, because LA is Z. I know, it's a lot of stuff built on top of it. The idea is to make your life easy, because in terms of this nice parameter Z, the solutions are not so easy, not so hard to visualize. So this second equation up here, written in terms of that Z variable, looks like this. And we want to solve this for the allowed values of Z. When is the left-hand side as a function of Z equal to the right-hand side as a function of Z? And since we know what tangent looks like as a function, right, let's divide both sides by Z and graph both sides, right? So we should see a graph of the tangent. Here's our graph of the tangent now. So what I'm graphing is not these two sides, but divide both sides by Z. Here's our graph of the tangent shown in the solid curves, right? Your usual tangent snaking through those values. Snakes through the origin, which is right down here, right? So this is just the positive Z values. And then if we graph this square root divided by Z, well, that's some funky looking function that we don't really have any intuition about. But if you graph it, here's what happens. And it's going to be a function of V0, the depth of our finite well. For smaller V0, it's a function that has, vertical asymptote there, and it comes down to the origin there. For larger V0, it tends to come down at larger and larger values. And we're looking for when these two sides are equal. So if we're looking at a medium V0 value, there's going to be 1, 2, 3 values of Z at which the left-hand side is the right-hand side. That would just be much harder to do if you wrote the whole thing in terms of E, because we would have so many constants around, it would be really obscure what you were even looking at. So even though we don't really know how to think about Z here, it just makes visualizing the solution much easier. So in terms of Z, we can see the allowed values of Z. They depend on V0. The bigger V0 is, in other words, the deeper our finite well is, the more bound state solutions we're going to have. But we're always going to have a finite number because that square root divided by Z always goes down and hits 0. And for positive Z values, both the numerator and denominator will be positive, and that means it can't go below. Okay, so what we're showing in the dash curve is the right-hand side after we've divided by Z. And now that we found the allowed values of Z, at least visually, we can rewrite what Z is in terms, Z's definition was LA. Oh, I forgot to put an A in here. There should be an A out in front of here. And L's definition is here in terms of the square root. So that tells us if you know a value of Z that you've gotten from the picture or from your graphing calculator, then you can turn that into an allowed value of E. See, I did this too much in haste today. I missed a parentheses over there that should be closing the other one. Okay, so depending on the size of Z0, and Z0 depends on the potential energy well depth. There may be many bound states, but there can't be fewer than one, because this branch of the tangent function always crosses at least that other side of the curve at least once. So there's always at least one bound state, but there could be 2 or 3 or 4, any finite number of bound states, depending on how deep the well is. It also depends on A too. Okay, yeah, let me just pause for a second because I feel like I've been talking nonstop the whole period. Any questions before we go on? All that is bound state solutions. What are the allowed energies? That's all we found out so far. And it's sort of an obscure method. The other question is, well, we took the two expressions, the one for continuity and the one for the continuity of psi prime, right? And we divided them. So it seemed like we threw away some information to get this the relationship we've been working with. What about the relationship between F and D? Well, I can go back and require just the continuity there. Once I know what L and kappas are allowed, I can solve for the relationship between F and D in those cases. And then once I've solved for the relationship between F and D, I can normalize the whole state, integrate from minus infinity to infinity. So we get the relationship. We've assumed it's a symmetric state, so we know how to get it for x less than 0. We've just been working on the x greater than 0 part, but x less than 0 part should look symmetric relative to it. And when you assume that, in this case, we assumed even solutions. If you assume the odd solutions, you'll get the rest of them, and everything works out no more of a complicated way than it does here. Okay, so those give us just the bound state solutions. Now we still got to work on the scattering solutions. Oh, but before we do that, this is a good thing to take a little break on. Let's look at my favorite Java applet here. So here's something that's indicating the finite well. Let me throw away some of this stuff here. Okay, so we've got the probability density as a function of position down here. It's in the ground state, which is just, a single hump kind of function. And then as I go upwards from the ground state, there's the ground state. psi shown in yellow. First excited state, you know, sines and cosines. There's the sine. Next one up is a cosine in the middle. Next one up is a sine in the middle. You can see it's sines and cosines in the middle, and then exponentially decaying away to 0 very quickly on the side once you pass the edge of the well. I can't really point over there, but you can see it just very quickly goes to 0 when you pass the edge of the well. And as I decrease the well depth, you can see the allowed energy solutions are shown by these white lines here. As I decrease the well depth, there's less bound states. The bound states have to have energies that are between minus V0 and 0. And so you can see less and less of them fit in there as I decrease the well depth. Same thing with the well width. As I make the, you know, that A value smaller and smaller, less bound states appear. So when I have a very narrow well, it's getting down to the point where we might only see a single bound state. And that's just like the delta function well that we saw before, where only a single state appears there. Okay. Scattering states. Well, they're no less confusing or, you know, just algebraically kind of annoying. That's why we're doing this as the last example. Right? But we want to make sure that we understand the details here, not because you're going to be forced to do the details on the next exam, but, you know, a simpler problem might involve the same kind of reasoning, but not in such extraordinary, you know, detail. And so you'll see some on the homework assignment where you're finding scattering states, and you have to do the same kind of things, but it's much simpler because I cooked up a simpler problem. Okay, scattering states. That means where the energy of the state we're looking for should be up here above V equals 0, right? Those kind of states. And that means it's oscillatory in all three regions. Now, because we're going to interpret x less than minus a and x greater than plus a as being the regions where we have some sort of beam that's either coming in or it's being scattered away, just like we did for the delta function well, we're going to keep those as complex exponential kind of traveling waves, right? This doesn't have the time dependence in it, but when we put in the time dependence, those would be waves traveling to the right and to the left. Same thing in the positive x region. In the middle, it doesn't really matter which way you put it as complex exponential functions or cosines and sines, but we're going to try to get rid of these constants c and d, because when you're doing a scattering experiment, all you're measuring are, you know, things that are related to the amplitudes of the incoming and outgoing beams. We want to know how much scattered and how much scattered forward and how much scattered backwards when you're doing a scattering experiment. So we're really going to get rid of these c and d's, and so we're just going to keep them as sines and cosines right now, okay? And there are these same parameters that come into it, except our kappa is now a k. There's no minus sign under the square root there. 6 unknown constants, okay? But we're going to apply boundary conditions. Of course, you know, everything's nice and continuous, so we have 2 boundary conditions at plus or minus a, right? So that's 2 equations, and continuity of the derivative at plus a and minus a is 2 more equations. And just like before, we're going to assume we're doing a scattering experiment where the beam is coming in from minus infinity toward the origin. And so we're going to assume that this coefficient that corresponds to a positive x region where the wave is traveling left, that would be an incident beam coming from the other side. We'll assume that g is 0. Okay, so throwing away the g term. And now there's a bunch of algebra that's not shown. And the question is, well, with these 5 constraints, one of which is shown here, so we've got 4 more constraints after I throw that one away. What do we want to get rid of all these coefficients that are out in front? And the answer is, well, we certainly want to get rid of the c and the d, because we don't know anything about c ahead of time, and we don't want to know anything about c or d. They just have to do with details of what's happening inside the potential. They don't have anything to do with the amplitude of a scattered wave in either direction or the amplitude of the incident wave. So we want to eliminate C and D. That's one of our goals. So two equations can be used to eliminate the C's and D's and express them in terms of A, B, and F. And then we have two more remaining relationships that can be used to express the outgoing waves away from the origin, their amplitudes, F and B, in terms of the incoming wave amplitude, A. And you just grind it out, and you know, it's not too bad. I've done it before, but you know, it's not something we certainly would not want to do it together as a class. And you find out that B is this function of F. B is proportional to F, and F is proportional to A. So that means I've written F in terms of A, and if B is written in terms of F and F is written in terms of A, I could write B in terms of A. So both B and F are, you know, sort of written in terms of A there. So using all those equations, we can write these coefficients that are in front of all these parts of the functions all in terms of A. So there's only one undetermined constant there, A, in terms of the coefficients of those. Okay. Remember, here we don't have to worry about what are the allowed values of K. All positive Ks are allowed, right? So we're gonna, you know, sort of parameterize this just in terms of K right there. So we're not thinking of, I've got to determine the allowed values of K. Every K greater than 0 is going to be allowed. Once I've found those, what I can do is calculate the magnitude of F squared over the magnitude of A squared. That's the amplitude of the transmitted wave to the amplitude of the incident wave, and that's what we're going to call the transmission coefficient, and of course the reflection coefficient. You could either calculate separately, or you could say, well, it's got to be 1 minus the transmission coefficient, since every particle is either going to go forward or go backwards. In one dimension, there's nowhere else to go. Okay, so now we've got these transmission and reflection coefficients. What do they look like as a function of energy? The energy's hidden inside the K's and the L's there, which are appearing all over the place. So it's kind of a complicated function, but you could MATLAB it, or here I just took it out of Griffith's. I think this is his plot. In any case, something equivalent is in his book. So I've got K and L are functions of E, and we're going to calculate T and R as a function of E. And here's the transmission coefficient as a function of the energy of the particle in the beam, or the energy of the scattering state. And the transmission coefficient is such that when the energy of the beam is just above 0, everything essentially gets reflected. Nothing gets transmitted. But then at a certain range of energy, it goes up to 1, and then it sort of oscillates there, but gets closer and closer to 1 with every oscillation. And you can kind of think of that as when the beam's coming in to that finite well, it's sort of like bouncing off the parts of the well, and you get some superposition of those bounce states, and that's going to cause there to be constructive and destructive interference for certain kinds of wavelengths. In other words, certain Ks will constructively interfere for the transmitted wave, and certain other Ks will destructively interfere for the transmitted wave, just like you have for a thin film on a piece of glass, right? We try to get the right thickness of that thin film so that you minimize reflection or transmission, whichever you're concerned with. All right. I do want to stop in just a second, and I wanted to check that we're down to something different. And so the rest of the chapter, what we're going to do is, in Griffiths, you're at the end of the chapter. We're going to do 2 more things, really 3 more things. We're going to talk about, well, what if you have a potential that you can't do anything analytic with? You could still qualitatively sketch correct solutions to the time-independent Schrodinger equation. We're going to talk about some rules for how to do that. We are going to talk about some ideas that will help us introduce some ideas that are going to appear in chapter 3. And then we're also going to do some MATLAB, which has to do with, you're going to choose some other potential that we haven't talked about yet, not the harmonic oscillator, although that might be a good one to try just to check your work, because you know what the solutions look like. And you're going to find, what does the psi corresponding to the ground state, first excited state, n equals 6 state look like for your potential? You know, maybe it's a quartic potential rather than a quadratic potential, right? Or maybe you do something that has some weird wiggle in it and then goes up like that. We're going to solve for those on MATLAB, and we'll talk about how to start that on Friday. And then there will be kind of a, I don't know, 1 or 2 weeks where you can work on it, and maybe we'll come together again just as sort of a help session to figure out MATLAB. But the idea of the first session is to get you started. If you're not warmed up to MATLAB, that's the time to get warmed back up to it if it's been a while since you've been using it. All right, let me hand back the exam. I haven't put the solutions on the website, but I hope to. If not in this next hour, then it would be before I leave at 5 today. And Alvis, I'm going to have to, I've got yours scanned in. I've just got to send an email to you with yours. Yichen. Tanner. Jake Fowler. Riley. Jake Woosley. And Mackay. I don't think I have any general comments about the exam, but maybe you guys can look at the solutions, and I'm happy to answer any questions either inside or outside of class about the details there. The median, I think, was an 85 or 86, so it was pretty high median for for an upper level quantum mechanics class. Let's just put it that way. So good job with that. If you didn't do so well, let's set up a meeting to talk about where to go from here and sort of, but the first thing I would do is look at the solutions and make sure that you're understanding what I was trying to get at in the problems, and then we can talk about strategies later on. Finally, enjoy your break day on Wednesday. I'm looking forward to it. It's my daughter's 11th birthday, so it's a good break day for me to have. See you next time.
Have a good day.
Okay, and I was going to stay for a little bit and talk to Yichen at least about homework. So if anybody else has homework questions, we can do that for a few minutes too.